in this video, we're going to talk about Euler's method. We're going to talk about what it means, how do we use it, and we're going to go through a few examples. So Euler's method is an approximation for solving a differential equation. So typically this is if you have a differential equation that is not separable, we still want to be able to find an approximation. So for number one, they're going to ask us to approximate y of 2. So Euler's method is a way for us to find an approximation when we cannot actually solve the differential equation. To use Euler's method, it says we're going to use linearization with a series of course corrections by recalculating the point and the slope. We'll show you a visual of this in a minute. For a little bit of notation, if x equals a is our initial value and x equals b is our desired x value, then we're going to want to find our delta x, which is the length of each step, and we're going to make that b minus a over n, where n is our number of steps. For Euler's method, most commonly we use a chart to organize our work. You don't have to use a chart, but like I said, most commonly that's what we do. There are also a couple different ways to do the chart. I'm going to show you one way. I feel like this way makes the most sense. So let's start with an example. Number one says, given the differential equation dy dx equals x minus 2 and y of 0 equals 5, find an approximation for y of 2 using Euler's method with 4 equal steps. Now, I want to point out this first differential equation, yes, it is separable. So yes, we could solve this using separation of variables. But I wanted to start with a simpler example. And I also think it'll be interesting to find our approximation in part A. And then in part B, we're actually going to solve the differential equation, and we'll see how close to the actual answer we got in part A. But before we do the example, let's show you what we are actually doing. So I have a visual for us. So this is on Desmos. So we are starting with, they gave us the point 0, 5, and they want us to approximate y of 2. Now, Euler's method is always in the context of a slope field. So if 0, 5 is on our graph, we can see right here, y of 2 is going to be 3. So this is the point that we want to approximate, but we are assuming that we cannot just get 2, 3 without doing some sort of approximation. So the first thing we're going to do is we're going to find a tangent line for our graph at x equals 0, y equals 5. So here's going to be our tangent line. Now I want you to notice if I use this tangent line to approximate y of 2, I'm going to extend this. Our approximation would be that y of 2 equals 1. And we can see that that's pretty far off from our y of 2, which we know actually equals 3. So in order to get a more accurate approximation, what we do is we say, well, let's pick a point somewhere on my tangent line. So we're going to pick this point. This point is 0.5, 4. And let's draw another line in our slope field. And that will give us a more accurate approximation for our y of 2. Now we can see again, if I extend this line to x equals 2, I'm still pretty far off from my y of 2 equals 3, but notice we're quite a bit closer to what we would have estimated if I had used that original tangent line. So for Euler's method, we again will choose another point. Let's move this back though. This is that. So let's choose another point. This point is going to be on the purple line. Let's draw another line in the slope field. Notice we're getting closer and closer to, more accurate to our actual y of 2. Now pick a point on the orange. Draw another line that follows our slope field. And then we can get a more accurate approximation. So this is what Euler's method is doing. Each of these new lines is what we call a correction, and we're going to draw another line in our slope field. Now, how do we decide? So I said pick a point on the line and draw another line in the slope field. How do we choose what point? That's going to be our delta x. So over here, we said that our delta x is b minus a over n. That's going to tell us how far over should I pick a point on the line. So that is what we are doing for Euler's method. So let's go through this example. All right, so let's start with, we are starting at y of 0 equals 5. Whatever point they give you is where you are going to start. So I have the point 0, 5. And next, let's find our delta x. So we know delta x is b minus a over n. So I'm starting at x equals 0, and I'm ending at x equals 2. So I'm going to say 2 minus 0. And they told us they want 4 equal steps. So that means that n equals 4. So that means each delta x is going to be 0.5. So I'm going to have my original line. That's going to be my first row of my chart. But my second line, I'm going to have a point where the x value is 0.5. And I want to increase in my chart by my delta x up until I get to 2. So I'm going to have 0.5, add 0.5 again, we get 1. Add 0.5 again, we get 1.5. Add 0.5 again, and we get 2. And you want to stop when we get to our ending x value. So given xy, we're going to figure out our dy dx. So plug 0 and 5 into dy dx. I'll show the work over here. That's going to be 0 minus 2, which is negative 2. And we're going to write an equation for a line. Now, lots of ways to do this. I'm going to start with point slope form. But I'm going to add this y1 over to the other side. So all of my lines are going to be in this form. So when I write my equation of my line, I'm going to say this one is y equals, my slope is negative 2, x minus, and my point is 0, 5. To get your new y value is going to go right here. To get that value, we need to plug in 0.5, because keep in mind, we want to pick a point on this original line to draw my new line, to do that first correction. So I'm going to plug 0.5 into my line in the line above. I'm going to have negative 2 times 0.5 minus 0 plus 5. When I simplify that, that's going to be negative 1 plus 5, which is 4. So 4 is going to be my y value for that point on that first line. And you're going to continue this process and fill out your chart. So now figure out your dy dx. It's going to be 0.5 minus 2, because dy dx is x minus 2. 0.5 minus 2 is negative 1.5. Write your equation of your line. X minus 0.5 plus 4. Plug in your next x value. That's going to be 1. I'm running out of room here. So I'm going to get negative 1.5. 1 minus 0.5 is 0.5 plus 4. I'm going to move some of my stuff over. Okay, when I simplify this, I get 3.25. Continue the process. So I'm going to find my dy dx. 1 minus 2 is negative 1. Plug in to get your line. To get your new y, plug in your x on your next line. So negative 1.5 minus 1 is going to be 0.5 plus 3.25. This is going to be 2.75. So you can see this gets a little bit tedious. But my new dy dx is negative 0.5. All right, to get my approximation for y of 2, we're going to plug in our 2. 2 minus 1.5 is 0.5. And when we simplify this, we get 2.5. So we think y of 2 is approximately 2.5. So to write out your final answer, you're going to write that. Y of 2 is approximately 2.5. And that is our answer using Euler's method. Now, we did say that this diffEq was separable, so let's rewrite our diffEq. Let's separate the variables. I'm going to multiply both sides of the equation by dx. I'm going to integrate both sides. The left side I'm integrating with respect to y. On the right side I'm integrating with respect to x. We know that the point 0.5 is on my particular solution, so let's plug in the point 0.5. And these two terms equal 0, so c equals 5. So here's my particular solution, but they want us to find y of 2. So we're going to plug in 2 and simplify from there. So I get 2 minus 4 plus 5, which is negative 2 plus 5, which is 3. So we know y of 2 equals 3, which we did show on the picture that we showed at the beginning of the video. But that is the actual answer. So we can see we got somewhat close to the actual answer. Let's do one more example. For this one we have this differential equation. Let's see. We have our initial condition f of 0 equals negative 2. They want us to use Euler's method starting at x equals 0 with a step size of 1/2 to approximate f of 1. So for this one, they're telling you that your delta x equals 1/2, and we're starting at 0. So I'm going to start at 0, negative 2. And I know that my delta x is 1/2, so I'm going to have 1/2. And then I'm ending at 1. So this one only has 2 steps, so kind of nice. Let's follow our steps again. First thing is I'm going to get my dy dx when x equals 0 and y equals negative 2. So that's going to be 0 minus 4 plus 1, which is negative 3. For my line, y equals m times x minus 0, which is just x, minus 2. To get my new y, I'm going to plug in 1/2, so negative 3 times 1/2 minus 2. When we simplify this, we get negative 7/2. Repeat the process. Get your dy dx when x is 1/2 and y is negative 7/2. Simplify 3/2 minus 7 plus 1. That is going to be negative 9/2. So write out your line. My slope times x minus x1 minus 7/2. Plug in 1 to get our approximation. 1 minus 1/2 is 1/2. And when we simplify this, we get negative 23/4. So we would say, this is our answer. We're going to say f of 1 is approximately negative 23/4. Let's look at part B. Part B says, let g of x be another solution to the same differential equation. Now our initial condition is g of 0 equals k. where k is a constant. Euler's method, starting at 0 with a step size of 1, gives us the approximation g of 1 is approximately 0. Find the value of k. So this problem is interesting because we're still using Euler's method, but we're using it in a little bit of a different way. So let's fill in the chart with what we know. We know we're starting with 0k. We know k is a constant. We have a step size of 1, so that means that our delta x is 1. So if I start at 0, increase by your delta x, we have 1. And they're telling us our approximation g of 1 is 0. So we have a step size of 1, and we also only have one step. So let's fill in this first line and see if we can figure out what k equals. So I want you to keep in mind our differential equation was, let's rewrite it, 3x plus 2y plus 1. So using x equals 0, y equals k, we get 3 times 0 plus 2k plus 1. So our dy dx is 2k plus 1. That makes our line y equals my slope times x minus 0, which is just x, plus k. And then to get my new y, we would plug in 1 for x. So we would get 2k plus 1 times 1 plus k. And I'm just going to say this equals 2k plus 1 plus k, so that's going to be 3k plus 1. But we know that whatever we get here for our new y needs to match this number right here. So we can say 3k plus 1 has to equal 0. Solve for k. K is negative 1/3. And that is our answer. So this is an intro to Euler's method with a couple of examples. Thank you for watching.